Hello again, students. Today we're going to continue studying systems of three equations, and we're going to do so with three additional examples. Alright, so our first example, I have my three equations and my three variables, so I'm just going to go through the same process like I normally would. Be organized in your work. You don't have to do it the exact same way that I'm doing this. Okay, but the reason why I like to label my equations 1, 2, and 3 is so that I can keep track of which equations I'm using and then which variable I'm going to eliminate. Alright, so you get your choice. It doesn't matter which variable you work with and which equations. I am going to use what looks easiest. I'm going to use equation 1 and equation 2, and I am going to eliminate y. Alright, so if I want to eliminate variable y in equation 1 and equation 2, I would have to multiply equation 1 by negative 2. Alright, so every term gets multiplied by negative 2, and that's going to give me negative 4x minus 2y plus 6z is equal to negative 10. And in my second equation, it can stay the same as x plus 2y minus 4z is equal to 7. I'm ready to add my two equations together, and that's going to give me negative 4x plus x, which will give me negative 3x. My y's eliminate because I made them so they had the same number in front with opposite signs, called additive inverses. And then 6z minus 4z will give me positive 2z is equal to negative 3. So this produces a fourth equation, so I'm going to label it as a 4. And notice that this equation only has x and z in it. So what I want to do is get another equation that only has x and z. So once again, I'm going to need to use two equations from the very beginning, and I'm going to need to eliminate y. Now I already used equation 1 and equation 2, so now I'm going to use equation 1 and equation 3. Once again, I have to eliminate y because I chose to eliminate y here. I need to get another equation that just has x and z in it. So to eliminate y, I need to multiply the first equation by negative 3. So that's going to become negative 6x minus 3y plus 9z is equal to negative 15. My third equation stays the same at 6x plus 3y minus 9z equals positive 15. I'm going to add my two equations together, and negative 6x plus 6x actually eliminates. Negative 3y plus 3y, this was the one that we were trying to eliminate. These also eliminate. And 9z minus 9z also eliminate, leaving me with nothing, so I'm going to put 0 on the left-hand side. I still need to evaluate the right-hand side, and negative 15 plus 15 is also 0. Remember, when your variables eliminate, if what you're left with is true, that's going to give you infinitely many solutions. Now, it's not all solutions, but in this case, it's infinitely many solutions, because if you have your planes that intersect, they could intersect on a line, and there are infinitely many points on a line, or they could be the same plane, and there are infinitely many points in a plane. Alright, so this was true. There are infinitely many solutions. Let's take a look at another example. Okay, so once again, I'll go through and be organized. So equation 1, equation 2, and equation 3. And then I'm going to look ahead, and I'm going to see which variable would I like to eliminate. So it looks like x is going to be a pretty easy one to eliminate. Alright, so I'm going to use equation 1 and equation 2, and I'm going to eliminate x. Alright, so equation 1 and equation 2, I need to multiply equation 1 all by negative 3. So that's going to give me negative 3x plus 3y plus 6z is equal to negative 12. Equation 2 stays the same. Now wait a second. Hold on, I just made an error. I was multiplying equation 1. I'm trying to eliminate 1 and 2. I'm eliminating x. That was a mistake. I apologize. I'm multiplying equation 1 by negative 2, and let's try all of that again. All right, so 3 times negative 2 is negative 6x. Negative 2 times negative y is positive 2y. Negative 2 times negative 2z is positive 4z is equal to negative 8. My second equation is 6x plus 4y plus 8z is equal to 11. I'll add these two equations together. The negative 6x plus 6x eliminates. 2y plus 4y will give me 6y. 4z plus 8z will give me 12z. And then negative 8 plus 11 is 3. So this gives me my fourth equation. Once again, I want to eliminate x, and now I'm going to use equation 1 and equation 3. Now this is where I need to multiply equation 1 by negative 3. And let's try that again. So negative 3 times positive 3 is negative 9x. Negative 3 times negative 1 is positive 3y. And then negative 2 times negative 3 is positive 6z equals negative 12. And then the third equation is 9x plus 6y plus 12z is equal to negative 3. All right, I'll add these together and my x's eliminate. This gives me 9y plus 18z is equal to negative 15. And that's my fifth equation. All right, so now I want to use equation 4 and equation 5. They are two equations and they both just have y and z, so two variables, so I have enough to solve. So I'm using equation 4 and equation 5, and what looks to be the easiest? I think I'm going to eliminate y. All right, so 9 and 6, the smallest number that those both go into is 18, so I'll need to multiply equation 4 by negative 3 and equation 5 by 2. So 6 times negative 3 would give me negative 18y. 12 times negative 3 is negative 36z, and 3 times negative 3 is negative 9. And then for equation 5, I'm multiplying everything by 2. So 9 times 2 is 18y. 18 times 2 is positive 36z, and negative 15 times 2 is negative 30. So I'm going to add my two equations together. Negative 18y plus 18y cancels. Negative 36 plus 36 cancels as well, leaving me with nothing on the left-hand side, so I'll put 0. And then I need to evaluate on the right-hand side, and I get negative 39. 0 is not equal to negative 39. This is false. And if you get a false statement when all of your variables eliminate, that means that there is no solution. There's going to be no point that can be found that is on all three of the planes at the same time. All right, so by now you figured out that these aren't just regular systems of three equations. These are irregular, which means that they might turn out to be infinitely many solutions or no solution at all. But here's another case of an irregular system of three equations. Now, right now it doesn't look like there are three variables because if you look at the first equation, it only has p and r. But as a system as a whole, we have p, q, and r. There are still three variables, which means I still need three equations in order to solve. All right, so I'm still going to label equation 1, equation 2, and equation 3. And then I'm going to pick two equations and eliminate a variable. All right, so I'm going to pick equation 1 and equation 2, and I'm going to eliminate p, which means I just need to multiply equation 1 by negative 1. So that's going to give me negative p minus 4r equals positive 7. But equation 2 I left the same. It's p minus 3q equals negative 8. All right, now notice something about this. When we try to add these two equations together, my terms are not all lined up. My p's are, but here I have an r term and a q term. These are unlike terms. They can't combine. So what I'm going to do is I'm going to rewrite this, but I'm actually going to put a placeholder in. So this first equation was missing q, so I'm going to put in plus 0q, and then minus 4r equals 7. My second equation was missing r, so I'm going to have p minus 3q, and then plus 0r equals negative 8. And now my system is lined up. So now when I go to add my two equations together, the negative p plus p eliminates. I have negative 3q, and then negative 4 plus 0 will give me negative, sorry about that, so minus 4r equals, and then 7 minus 8 would give me negative 1. All right, so once again, I produced a fourth equation. Now, if I tried to eliminate p, if I was just going through my process without thinking, I would go back and either use 1 and 3 or 2 and 3 to eliminate p. But there's a problem with that. Equation 3 doesn't have p in it, so I can't eliminate p. It already doesn't have it in it. So that means, notice that equation 3 has just q and r, and this equation that I just came up with just has the variables q and r. Okay, I just need to use equation 3 and equation 4, and I can solve my system, because these are two equations that have the same two variables. So I'll either need to eliminate q or r. It doesn't really matter. I'm going to eliminate q, so I need to multiply my third equation times 3. So that's going to give me 3q plus 3r equals 3. My fourth equation is still negative 3q minus 4r equals negative 1. I'll add these two equations together. So 3q minus 3q cancels. 3r minus 4r will give me negative 1r, and then 3 minus 1 will give me positive 2, but divide both sides by negative 1 and I get r equals negative 2. So I've gotten one of my variables. Okay, normally I'd have to just plug this back into the last equations that I was working with, but if you look up at your original equations, each of those only have two variables to begin with. So what I'm going to do is I'm going to plug in, or substitute in would be the better word to use, r equals negative 2 into my equations that had r in them. So I had equation 1 and equation 3. So plugging in negative 2 into equation 1, that's going to give me p plus 4 times negative 2 equals negative 7. So p minus 8 is equal to negative 7. Add 8 to both sides, p is equal to positive 1. Into equation 3, I have q plus r, which is negative 2, equals 1. So really this is just q minus 2 equals 1, so I'll add 2 to both sides and I get q equals 3. Alright, so this one does have a point that all three of my planes share. Now I need to write this as an ordered triple. Alright, so I need to write my numbers in the order that the variable that they're associated with is in alphabetical order. So that will go p, which was equal to 1, then q, which was equal to 3, and then r, which was equal to negative 2. And there you have it, solving irregular systems of three equations.